So this was our Lab6 experiment reaction, and I just wanted to go over how to look at the different analyses that we did and try to figure out whether the reaction went the way we wanted it to or not. We did an IR, we did a GC, we did NMR, so we have some data about the reaction. Let's see if we can figure out what to look for on these spectra. So biodiesel, we are making a methyl ester of a fatty acid. So this R group is a long alkyl chain here. So what exactly is that R group? The fatty acids, generally, most of them are fairly short, so between 51 and 18.5, so almost 70%, 3/4 of it almost, are either 12 or 14 carbon saturated fatty acids in the coconut oil. A few of them are shorter, so this 9% brings it up to like almost 80%, a little bit longer. So there's very few of the fatty acids that have alkene groups in them, so we are not expecting to see a lot of those. 5% for the oleic acid, another 1% for linoleic acid, so only about 6% of the fatty acids that are in coconut oil have an alkene, and so about 6% of the biodiesel that we make should have an alkene. So we're mostly just seeing an ester functional group. So thinking about IR, the functional groups, for biodiesel we would expect to just see an ester, and then mostly just CH saturated. Again, the alkene is only 6%, so we might not see a lot of that in the IR. Some of the side products that we could have, if we have any glycerol or methanol in our IR, we would expect to see some alcohol OH groups. We would also see alcohol OH groups if we had any monoglyceride or diglyceride from incomplete reaction. If a lot of moisture got into our reaction, we would be unfortunately making some soap molecules. These would look a lot like carboxylic acids rather than esters. So we would see a little bit of that as well. And then we have the triglyceride. We could have some leftover unreacted triglyceride inside our biodiesel. That is completely possible. And that would look very similar in IR because it has the same functional groups. It does not have any alcohol. It just has esters, which is the same thing that biodiesel has. So let's take a look at our IRs. So here is an IR of coconut oil itself. It has very similar functional groups to the biodiesel, so there's not much difference that you can tell. We still see an ester peak, a little bit above 1700, more like 1730 or 1740 wave numbers. Here is a drawing of coconut oil. It has an ester functional group just like biodiesel does. It has CH stretches below 3000. I have a line here for 3000, just like the biodiesel does. There's a small amount of alkene, not very much, so the IR is not really picking that up. And so mostly CH stretches and ester, same thing that you would see for biodiesel. So there's not a lot of difference between the IRs for those particular two compounds. Here is the IR of glycerol. So this is very different. This is just glycerol itself. So we do not see an ester at all, and we do see a very large OH peak. We still see some CH stretches as well. We have CH in the molecule. We have OH in the molecule. So if we had glycerol in the biodiesel, we would still see the ester of the biodiesel, but then we would also see some significant OH group as well. This particular IR is an IR of glycol stearate. We had a sample of that. I've drawn it on the screen as well. So this is an ester of stearic acid, so an 18 carbon fatty acid, but instead of a methyl ester, this is an ester of using the alcohol of glycerol. So this is a monoglyceride rather than a triglyceride. We don't have three esters here. We just have one ester on glycerol with a fatty acid. So we still have the CH stretches above 3000. We still have the ester. This time we also see a little bit of OH in the molecule because we have some OH groups here. So if you had some contamination in your biodiesel that had some of this monoglyceride in it, you would also be able to see some OH stretch from that. So here is an IR of a biodiesel sample. I tried to draw a line for 3000. It looks like most of the CH stretches, if not all of them, are below 3000, so there's not a lot of alkene present. That's what we expect. Also, it does seem like there is a strong C double bond O stretch. Esters tend to be above 1700, so around 1730, 1740. That is what we expect as well for an ester, and that is about all we see for the biodiesel. Of course, it is possible that this sample still has just coconut oil in it. Remember, the triglyceride is not something you would be able to tell the difference from the IR. All right, here is a sample of biodiesel that might have a tiny bit of contaminant in here with an OH group. There's a little tiny bit of stuff over here, probably not too much, maybe just a very small amount. So we could take a look at the GC and the we could take a look at the GC and the NMR to confirm that if we need to. This stuff over here is just some noise. Every once in a while, the IR baseline gets a little bit noisy, and if I don't re-zero it and too many students have gone taking their IRs, you might see a little bit of this stuff, but this is not really a signal here. Over here we have an IR that has a lot more of OH group. Obviously, pretty large amount, so there could be still some methanol in there, or maybe some glycerol got in there, or a significant amount of the monoglyceride. It's not just glycerol because we do have an ester peak here, so there is some ester, but it might be contaminated with a significant amount of water, methanol, or glycerol, because it seems to be quite a large alcohol here. So in contrast, this one does not seem to have any of the alcohol in the biodiesel. So those contaminants do not seem to be there. It still does have a little bit of this noisy region, but none of the alcohol. Also, if there were some kind of carboxylic acid, some fatty acid, or some soap molecules, you would expect to see a little bit more of a hump over here, which we don't see. So this one is looking pretty good. All right, let's look at an NMR of what coconut oil might look like. We have a triglyceride here, and I've circled some different areas or different types of chemical shifts that we might expect to see. We have about 5 protons, 5 hydrogens that are on carbons that have oxygens on them. So these would be in about the 4 ppm range. I have it color coded over here. So in this red area, this is about a little over 4, between 4 and 4.5 ppm. That is where an alcohol or ether or an ester type proton would be, something that's on a carbon that's on an alcohol. A little bit higher, around 5, is where you would see some alkenes. So I drew one alkene in this triglyceride. Coconut oil does not have very many. Remember, the unsaturated fatty acids only make up about 6% of the fatty acids that are in coconut oil. So instead of 2 protons here, we see a little bit less. We don't see very much of the alkene signal, too much at all. And then we have some that would be maybe kind of closer to 2 because they're next to a ketone. We have 2, 4, 6 protons that would be closer to a ketone. This is integrating a little bit high for that. And then down on the very end, the CH3, remember, those are the most upfield. So we would expect to see maybe about 9 protons over here. We're seeing about double that, around 18 instead. So there might be some contaminants in this coconut oil. But we see the rest of that, if you count up all these CH2 groups, there's about 70. And so we do see quite a bit of other alkyl protons, 82 and like 13 about, and 3. So that is 95, 98, so close to 100 protons rather than just 70. So this might have a little bit of contamination in it, but it's in pretty good agreement with what we would expect for coconut oil. And if we have some monoglycerides and diglycerides contaminating, or even coconut oil contaminating our biodiesel, we would expect to see this integration be rather high, like it is for coconut oil. Let's contrast that with the product, the biodiesel, what the integration should be for a sample of biodiesel. Let's take a look at the NMR for what the glycol stearate is showing. So this is again an example of a monoglyceride. We have glycerol, and instead of 3 esters on it like a triglyceride, we have 1 ester. We have stearic acid, the 18 carbon saturated fatty acid, as the fatty acid ester that's on here. So we do see some protons that are in that range where alcohol protons or protons that are on carbons that have oxygens. So up in that 4 ppm range, we do see some over here. So again, this is a little bit more complex. It has some more splitting. Rather than if it were just a methyl ester, the biodiesel, we would expect a singlet. These have neighbors. These protons, they're different, slightly different chemical shifts because they're different. This one's on the carbon that has the ester, this one's on the carbon next to it, the carbon that's 2 away, so they're not exactly equivalent like a methyl ester biodiesel signal would be. So that we do have some splitting, we have some more complexity here, and we have some different chemical shifts. So we have a more complex signal down at the 4 ppm range. And then the integration should be a little bit closer to biodiesel. So compared to this being about 5 over here, we would expect to see about 35. We do see a little bit more than that, a little bit higher higher integration than I would expect. So I'm not exactly sure why, but we would expect the integration to be a little bit closer to what we expect for the biodiesel, to have it be about 30-ish, 30, 35. So, but if you do see some more complex signals down in that 4 ppm region, then that could be some diglyceride or some monoglyceride contaminant in your NMR. Let's take a look at some NMRs that could have a little bit of contamination from either triglyceride or monoglyceride or diglyceride in them. Here is a sample of biodiesel that does not look like it has a lot of contamination with glycerol or a coconut oil or a diglyceride or monoglyceride because it has a pretty sharp 3-proton methyl ester. So for the biodiesel, we would expect this signal that's showing up in the 4 ppm range to be fairly sharp, a singlet worth about 3. So I was choosing a sharp singlet to integrate for 3 protons. And then in comparison, the rest of the molecule, most of biodiesel has about 12 to 14 carbon saturated fatty acids. So there's not that strong a signal in the alkene region. You can see that here. There's a little something integrating for about 0.1, nowhere near the 2 hydrogens that it would have if it had an alkene in it. At 100% of it had an alkene, you would expect 2 alkene protons, but we see a very small amount of alkene protons because only about 6% of this biodiesel has an alkene. So less than 10%. So 2, if it were 100% having an alkene, you would expect an integration of 2 here. 10%, you'd expect an integration of 0.2. An integration of a 0.1 shows that it's about 5% that has an alkene in the fatty acid. And then we have a total of about 25 to 27 alkane protons that are not in the 4 ppm region, maybe 2 that are close to 2 ppm. So over here we have about 2, a little bit more than that, maybe 3 or something down lower, and then about 20-ish in the middle here. We have about 25 here. If you add this 3 and this 20, we have about 25. So not a lot of extra alkyl protons from contaminants. In contrast, here is a sample of biodiesel that does have a little bit of contamination, either with triglyceride or diglyceride, monoglyceride, because remember that would have a signal in the 4 ppm region that's a little bit more complex than just a 3 ppm singlet. So we see the 3 ppm singlet here. We also see some additional signals that are not as sharp a singlet. We have a little bit of splitting here, a little bit of other signals here, so that might be coming from some of these type of signals that are on glycerol where they have neighbors that split them. There's a little bit more alkene as well, which we saw in the coconut oil. It was a kind of a larger percentage of alkene than expected, so maybe there's a little bit of coconut oil here in this sample. Also, the fact that there is more alkyl signal here than we're expecting. Remember, we expect about 20 to 25. We're seeing 50. So that is more in line with having a little bit of extra fatty acid in there. Some diglyceride, some maybe some monoglyceride or triglyceride. So we have a little bit of contamination based on the integration and based on the presence of some additional signals in the 4 ppm region that should not be in clean biodiesel. All right, so I just wanted to remind everyone what this GC trace means, because it's been a while since we used the GC. This x-axis over here is the time. We have a little label over here. It does not start collecting data until 2 minutes. So there's a 2-minute delay. That's why this doesn't start at 0. It starts at 2. And at 2 minutes, it starts collecting data because the solvent comes off before 2 minutes, and we don't want to overload the detector with lots of solvent. So every second or couple times a second, it is scanning for the number of ions hitting the detector. The mass spec itself is the detector. And so when there's not much happening, there's not a lot of ions, when something does come off of the GC column, we do see a spike, an increase in the abundance of ions that is hitting the detector. So this is 6 times 10 to the 7th, which is 60 million ions from, maybe just at a background level could be just 10,000 or something ions. Then we have 60 million all of a sudden hitting the detector. So that is one of the components of the mixture coming off of the column. So the column is separating this biodiesel into, it looks about 7 substances, 7 compounds are coming off, and that is not too surprising because coconut oil is not just made of one fatty acid. So when we make methyl esters of all the different fatty acids, we have several different ones that we can see coming off of the instrument. So these are all different biodiesel molecules, and the GC separates according to boiling point, which since these are all similar types of compounds, the boiling point is pretty much corresponding to the mass. So the lighter ones are coming off first, the heavier ones are coming off last. So for each student, I just printed out one scan, one of these time points. So each point along this trace is a scan. I only picked one of them. So for this particular student over here, it looks like I picked scan number 701, which was at 5.7 minutes. That is underneath this peak over here. That's where I took the scan. For different students, I was choosing maybe this large peak or one of these peaks over here. A couple students, I chose this peak. So it was pretty random as far as which peak I chose to print out on your GC printout that you're getting. So if we look at scan number 701, again, at about 5.7 minutes, we have 120 million ions hitting the detector. Some of them are the methyl ester that has not broken into pieces, and some of the things that are hitting the detector are the methyl ester breaking into pieces because it's being bombarded with a stream of electrons, and so that's very high energy, and not all the molecules stay intact in this process. So some of the molecules are staying intact. The highest molar, the highest mass that's detected is the entire molecule weighing 270, and then a lot of the molecules are breaking into pieces. So the fact that there are a lot of peaks here does not mean that your compound is impure. It just means that your compound is breaking up into lots of different pieces as it hits the detector. There are hundreds of millions of your molecule, and not all of them stay in one piece. Some of them do. About 3 million stay in one piece, but a lot of other millions are breaking into pieces before they hit the detector. So having a lot of peaks here means that you have several different components in your mixture. Having a lot of peaks here does not tell you how pure your compound is. This is just a snapshot that is one scan happening at 5.724 minutes, and that is a bunch of millions of compounds getting bombarded with electrons. All the same component, all the same molecule are being bombarded because they're all coming out at the same time, and then some of them are surviving that bombardment and some of them are breaking into pieces. That's what's happening there in the GC. So the absence of peaks past the 7-minute retention time means that it does not have a lot of coconut oil residue, triglycerides, diglycerides, monoglycerides. Also, there's not any of the contamination that we've been seeing in the hexane for some of our samples. This is a GC run of just the hexane that we were using. I have a student hexane run, and there is a lot of noise, a lot of contamination down here in this region below 4 minutes. So it was coming off of the column. Between 2 and 4 minutes, there's just a lot of contamination. I'm not exactly sure why. Not all the samples had it, but especially Wednesday and Thursday samples, we did have some of that. And then, so here is a run of students' sample. And so here we have the peaks that are due to the biodiesel. So the biodiesel itself is probably not contaminated. A lot of times the contamination for the biodiesel comes off after 7 minutes. So if we have some coconut oil or some diglyceride, triglyceride, you see peaks over here, which we are not seeing. And this is just coming from the hexane, so I apologize for that. A lot of these GC traces don't look as clean as you would expect. Here we see a GC sample where there is some contamination with some larger masses that are coming out after 7-minute retention time. So probably some other residue from coconut oil itself, some partial hydrolysis, partial transesterification, of the coconut oil. Some diglycerides and monoglycerides are probably present in this sample over here. Here we have a sample that is free of the coconut oil contamination, but the hexane that was used unfortunately had a little bit of contamination, but this would count as a fairly clean biodiesel sample. It's just that the hexane had some other stuff in it, so this I wouldn't worry about this type of a trace either. Here is a sample where we see both. We see the hexane contamination, and we also see a little bit of coconut oil contamination as well. So there is a Canvas page called GCMS of biodiesel, and I have a table with the different peaks that are coming out, these different retention times. We were just looking at the 5.7 minute peak, noticing that the largest mass was 270, and we were looking for a peak that was at 239, and that is present. This is just some lists that I made a previous year, so the label came out better on that one. So 239 is the 270 minus 31 is something that you see. A lot of these peaks are the large mass with a loss of 31. I also have some links to pages that talk about how to interpret the GC mass spec of fatty acid methyl esters. So let's take a look and see why we would see a loss of 31. Oh, here is one that happens to be 270. So we have methyl stearate. The total mass is 270. That's your M value. If you get a McLafferty rearrangement, this piece over here breaks off and you get a piece that weighs 74. If the methoxy piece breaks off, you get 239. So here is a diagram showing where the mass of 74 comes from. We're starting with methyl stearate with a mass of 270, and then a McLafferty rearrangement gives this positively charged piece, and this is the same no matter what the R group is. So it could have been stearic acid, it could have been oleic acid, it could have been any one of the fatty acids. This piece will change depending on what fatty acid you're using, but this is not the positively charged piece. The positively charged piece that is falling off is this, and this is the same for any of the fatty acids. So we see a large peak at 74 for a lot of these fatty acid methyl esters. Here is a diagram that shows how you would get the mass minus 31 as a peak on your mass spec as well. So I have the example of methyl stearate, which weighs 270, and this time instead of a McLafferty rearrangement, I have a methoxy radical falling off. So the fully charged, or the full mass piece that is being detected by the mass spec is a cation radical, so we have one electron missing on the oxygen. If that splits off, like if that electron combines with an electron from the sigma bond, that would cleave this carbon-oxygen bond in a homolytic fashion. So this oxygen would take one electron, this carbon would take one electron, it would probably combine with this electron so that you have a triple bond of the oxygen here. This is still positively charged. So the piece that is positively charged is the one that has lost the methoxy radical. The methoxy radical has one carbon, 3 hydrogens, and an oxygen that weighs 31. So you could figure out the chemical formula of the piece that's left, or you could just subtract 31 and look for peak 239 on your mass spectrum as well. And so this applies to any other fatty acid methyl ester. You would take the mass and you should see that mass peak, and then you should also see a peak for that mass minus 31. So I hope this video helps you to make sense of all the different spectra and printouts that you have for your biodiesel sample, and good luck with the rest of the lab.